show up in this database if the database has a mutant form of this protein. And I've been on NCBI and I've been on CATH, and they've showed various forms of mutants. So that can be helpful in research. Go ahead and click Find My Sequence. Not structure, find my sequence. Go ahead and copy and paste that into the FASTA. Go ahead and search.
I chose the first sequence from the species Octodon digus because I have no idea what type of animal.
Octodon digus.
Octodon. That means 8-tooth. I can't imagine what this species is that's called Octodon digus.
The result is insulin-like subunit.
Well, you used the human one, right?
Correct.
And I used Octodon digus, and I got the exact same domain result that you did. So it didn't matter which species we used. Just narrow it down.
Those numbers, this is class, this is architecture, this is topology, and that is models. And it'll show up like this
How did you get that?
by clicking on the name.
Clicking last domain to JZA00.
Yes, correct. It's a perfect. Hold up. And Dr. Phelan, since you chose a different species, what you might want to look at is all the numbers that make up the CATH code. That is what the CATH code is called. If you're doing different proteins that might all have the same function, it might all have different CATH nodes. This is a domain though that matches. It showed in the previous page. It matched at about 80 some residues, and it matched about over 50%. And if you can click this little triangle on the bottom, you can actually see it in similar to Pymol C3 kind of thing. And if you're doing a lot of research, especially if there's an epidemic and you don't know what you're dealing with, if you do get the sequence, so you can run it through the database. And if I didn't know what the sequence was at all, I would run it through the database and it'd say insulin-like, subunit E insulin-like. So I have a pretty good idea that it has a lot to do with sugars and just sending the signal to break down sugars inside the cell.
Okay, so we have in that page then. So one is the what's C stand?
Class.
Class. So it's class, mainly alpha. And then its architecture is an orthogonal bundle.
Yeah, feel free to click on orthogonal bundle and see if there's a description of it.
It means two bundles that are like have an angle, they're angled toward each other, right? I think so.
I believe so.
Something like
You're going to see alpha helices in it for sure.
yeah, two alpha helix, one alpha helix, two alpha helices that have an angle toward each other. That's what orthogonal means. Exactly what angle it specifies it, you know. And then for the topology, it looks like its topology looks like that of insulin-like subunit E, and it's homologous to insulin-like. So that's why that's the same entry on those last two, is because the topology is like this protein, and as a matter of fact, its sequence homology is also like this protein. I guess that wouldn't necessarily be true, but they'd be the same. I wonder if it'd be fun to try to find something that didn't. It said its topology is like this protein, but its sequence is more like this protein.
I'm sure that exists.
I'm sure there's some of those.
Yeah, these numbers would be these numbers. The lower you go, the bigger range of numbers you can get. But with class, it's either going to be 1, 2, 3, or 4. If you go back this kind of shows how they all got evaluated. This is their score. The more negative the number, the better. Aligned length is how many residues it was. Percent identity, the first. So I guess this first one actually did 60%.
I'm sorry, I didn't catch how you got to that page.
If you go. Yeah, the page where you actually click.
Page where the CATH nodes are all listed down.
Before you click on the...
One more before that.
Before you click that, just go
Oh,
back.
back from there.
Yeah, see the very.
You're all eight matching. Got it.
No problem. So not only did it find this residue to be the most identical with 60%, but it also found other domains in the protein database. And if you're doing research, this of course would be important to you because these domains might have different functions.
How long was the sequence that we, like how many amino acids long? About 100.
Insulin's only like 100, if that.
So it says
There's a small guy.
It says aligned length 83, 83, for most of them 85, 77. So it chose to match them up for part of the sequence, and it recognized there's some parts that just don't match up, so it leaves them off the comparison. There's 100 amino acids, but they don't all always match, so it only chooses the part that's reliably matching, which we call local alignment.
What is CATH worth? I've been trying to go through this as I speak, but research, having the correct sequence, if you're trying to replicate a protein, and you know this protein to be on the database, and you know its amino acid structure, and then if you actually run it in the lab and it's different, you can have problems. So you use this as that. As a resource analyzing a mutant sequence, like I said, if you're sequencing and then you get a different amino acid, it might still form a protein, it might function differently. If it does function differently, there's a chance that it's going to be in the database part of some differences. Finding other proteins with similar functions regardless of homology. I found it interesting that it first takes the structure before it actually compares it to other species. That can be useful if your sole purpose in the protein is just to find a function, and it doesn't really matter if it came from a certain species.
Yeah, if you're not doing evolutionary studies, you're just doing biochemistry and protein function, that would be good. But I might add here, now I'm not asking the question, I'm just asking. If you are doing evolutionary studies, sometimes people are comparing two types of bacteria. Now, bacteria have been evolving for a long time, so there might be two species of bacteria that are more different from each other than we are from worms, or than we are more different from each other than we are from yeast. So, and those bacteria might be so far apart from each other evolutionarily. Now, they're still bacteria. It doesn't matter. Evolution happens even if you are still a bacteria. Those bacteria might be so far apart from each other evolutionarily that you can't find a similarity. You line up two proteins, and the amino acids don't match up. Yet their proteins still do the same functions, so they'll show up in CATH as similar structures. So it's a way to find some relatedness, even though there's hardly any vestige left of sequence. This does happen when you're trying to study deep evolution that happened 2 billion years ago, and you're trying to reconstruct what happened back then. This is the kind of thing that can help you do it. Sorry.
It's fine. What is CATH worth? Visualizing. You need to visualize polypeptide chain as tools of a protein. This is useful if you're into enzymatic research. because obviously the enzyme's going to act as a catalyst. It's going to function and do something, and the polypeptide chains are going to be the tools of the protein. So if you're singling out these different domains from a protein that you've sequenced, you can visualize and see how the polypeptide chains do what they need to do as a tool for the protein. And also finding cofactors and coenzymes, that's just different parts of the protein. Useful information for research. And that is it. One more thing. Let's see if I can bring it up.
Don't log off. I think we can do some playing with this now that Eddie showed us how to do it. I think we can do some playing. Go ahead.
Are these dot val?
Those are seen in 3D, yeah. Go ahead and open. You might have to choose, select the program. And I had to do this the other day. You better browse. Browse, and you're looking for NCBI folder. Delano Scientific has go back, scroll back up. See Delano Scientific, that has Primal. So go back. Now look for NCBI. NCBI will have CN3D. And if we do this on enough computers, we'll have computer.
This one only has one, but
One what?
amino acid, polypeptide chain for polypeptide. And if you actually click on that, it'll actually redirect you to NCBI.
Oh, that hardly ever happens. Well, that hardly ever happens. So this NCBI is used by people all over the world. But sometimes when when 10 of us in this room all try to do the same thing, we slow it down. Because it's hardly ever the case where 10 people in the world are looking at the same thing on this.
So if you do have a protein you're looking at, this is kind of a bad example, but usually, well, not usually, sometimes there's not just one, but there's 2, 3, or 4 different amino acid polypeptide chains for a protein. I had to select this one, so it's the only one. If you actually select the chain, you'll actually be able to see it. Just change color there. So say if you're interested in a polypeptide chain that's on the right side of the molecule, you want to find out maybe how it functions. Or if it's in the database at all. Simply click here, it'll redirect you to NCBI where you got it from. Then you can go to CATH once you have the sequence, do FASTA, sequence search. Once it loads, you get results. And it's not 100% the sequence identity. So it does that. And of course, you're viewing it in CN3D. If you click here, you can also view it. But don't forget that CATH offers similarities in the database according to the algorithm that they designed. So if you have multiple proteins, if you look at the CATH code, you can see the similarities between the 2 proteins and how far down the sheet they are. You just have to look at this final code. And if you're looking at different proteins, it might change here, it might change there, and then you'll get different domains, but at least you'll be able to see different CATH codes for the various domains. That's basically it. Any questions?
that's all